Welcome to our discussion of complex zeros and the fundamental theorem of algebra. Here are the objectives for this video. Let's start with the first one, and the one that from the title seems most important, a fundamental theorem of algebra. Now, it is fundamental as far as how algebra works, and it's a building block for a lot of things, but for most of you, this is going to be a who cares kind of moment. And it's also kind of a no duh kind of moment because we've already talked about this, right? We already know that if we have a polynomial of degree n, right? So let's say we have a polynomial of degree 7. We've already seen that the maximum number of real zeros, right? Zeros that are real numbers is 7, right? We can't have more than 7, but we can definitely have less. What the fundamental theorem of algebra does is it expands that concept and it says, well, yes, you can have up to 7 real zeros for a polynomial of degree 7, but if you count complex zeros and if you count multiplicity, right? So if you have a zero show up twice, so you have, x plus 1 twice as a factor. You got x plus 1 times x plus 1 times a bunch of other stuff. Then -1 shows up as a 0 technically twice, right? It's got multiplicity 2. So if you count multiplicity and you count in all possible complex zeros, then every polynomial of degree n greater than or equal to 1, which is really kind of silly because that's just basically all polynomials because we're not going to have a degree of 0 because that's just a constant, right? So basically all polynomial functions will have exactly the same number of zeros as their degree. Now this tells us that if it has complex coefficients, it's going to have at least one complex zero. And then it says, okay, because real numbers are complex numbers, because remember real numbers are a subset of the complex numbers because all they are is a complex number where the b part is 0. Right, refresh your memory. What are complex numbers? Complex numbers are something of the form a plus bi, right, where a and b are rational numbers, right, which are part of the reals. They're basically numbers that can be described by fractions. Well, the real numbers basically just are a subset of that because if you take away the imaginary part, you let b be 0, then you have a real number. Okay, well, when we couple this idea of at least one complex zero with the factoring theorems that we have and with the idea that we have up to and including numbers of real coefficients, then we get to this complete factorization theorem. And when we put all of that together, it's basically telling us that for every polynomial of degree n, we're going to have n many solutions, but some might be complex. So we still have less than n many real solutions, which are normally the only solutions we care about. So in application purposes, we normally only care about the real ones. This is just telling us that if we count up all the complex as well, we're going to have the same number of zeros as we have degree. All right, so here's a simple example. We have this polynomial of degree 3. We want to find all the zeros and completely factor it. Well, how you go about factoring it and how you go about finding zeros is up to you. Remember, I've said this before, that it can all boil down to the same concept. Anytime you have a polynomial of any size, any degree, any shape, whether it has all of these extra terms in the middle, or maybe it has, just the leading coefficient and just the constant. Sure, we have shortcuts that help us solve the ones that don't have the stuff in the middle. But, if you're having a hard time remembering when to use which technique, then just remember that they can all be solved the exact same way, right? Step 1 is find all of your zeros, right? Find all possible zeros. And remember, that just comes from P over Q, where P is factors of the constant, and Q is factors of the leading coefficient. So in this case, we would go, all right, factors of 3 are just 1 and 3. Factors of the leading coefficient are just 1. And it tells us that our only possible zeros are plus and minus 1 and plus and minus 3. And then step 2, right, after you figure those out, step 2 is always just guess and check. It's all about running through your list. We've got 4 possibilities there. Let's just start ticking them off, right? Try one at a time, and we have all these great tools to help us. We know that we have the remainder theorem, which tells us, if it's a 0, then we can plug it into the polynomial and the remainder will be 0. Kind of duh, right? So the easiest way to check to see if it's a 0 is you can just start throwing them into the polynomial and see if you get an answer of 0. And then when you do, you go ahead and do either the long division or the synthetic division to reduce your polynomial. And then you start thinking, well, that's kind of a wasted step. Why don't I just go straight to long division or straight to synthetic division and just start trying it with all of these, right? So you take your polynomial, you write out the coefficients of 1, minus 3, 1, and minus 3, and you start with 1. You go, I'm going to try 1 first, right? And I bring down my 1, multiply, add, multiply, add, multiply, add, and you go, nope, 1 doesn't work. And then you move on and you try something else, right? And you go, hey, negative 4 is, a fair distance from 0. So if 1 doesn't work, negative 1, which is kind of close to it, probably also doesn't work. So instead, I would try 3 next. And then 3 is going to work, right? So these are all done the exact same way. So when you see these examples where they all of a sudden factor by grouping, and you're like, oh, how am I going to know to factor this one by grouping? Well, you might not. And if you don't, do it the standard way, right? All of these are just shortcuts. If you recognize that you've got a 1 and a negative 3, a 1 and a negative 3, right, as far as coefficients are concerned, then that's a pattern. And when we have a pattern, grouping by terms often helps us factor kind of more quickly and more efficiently. But you'll get there anyway if you just do the long division or synthetic division. All right, so we'll run through this really quick. We factor by grouping, and then that enables us to factor out what was in front of each of those x minus 3's. Now we have our polynomial factored into 2 terms, one of them being linear, right? The linear term is the one that doesn't have any power of x. So that part's done, and that tells us that we have a factor of 3, right? This should be moved over here so it points correctly. So we now have a factor of 3. The other one, x squared plus 1, if we set that equal to 0, right? Because ultimately that's what we're doing with these things. We're setting them equal to 0. If we have each of our factors, set equal to 0, then we get x squared equals negative 1, which is impossible in the real world, but imaginary numbers, we get plus and minus I. And so those are our other 2 zeros. So there are 3 zeros, right? Power of 3, right? Degree of 3, 3 zeros at 3, I, and negative I. And then here's our factors. X minus 3, x minus I, and then x minus the negative I, which of course reduces to x plus I. Okay, so next we're going to talk about zeros and their multiplicity. We already know, or we should already know, what it means to have multiplicity. It just means that that 0 shows up more than once. And what that really just means is that the factor, right, that creates that 0 has a power. It's there more than once. So for instance, this polynomial example here, x minus 1 cubed, blah, 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 blah. We can see that because x minus 1 is cubed, that first 0 of 1 actually shows up 3 times, and so it has a multiplicity of 3, and so on and so forth. And in fact, what would be the degree of this polynomial? If you multiplied that out and actually had your polynomial, what would the degree be? And hopefully you're all going, well, 3 plus 2 plus 5, that is going to be degree 10, right? So your leading coefficient is going to be x to the 10. So it should have 10 zeros. Well, here's 3, 4, 5, and 5 more is 10, right? It technically only has 3 zeros, the numbers 1, negative 2, and negative 3, but because of their multiplicity, right, in a technical sense, there are 10 of them. So it holds with that idea that the number of zeros matches the degree. So here's where we put it all together and we go, now we have this theorem that tells us for all polynomials, again, of degree n greater than or equal to 1, you go, well, no, duh, that's just polynomials, that has exactly n zeros, provided that a multiplicity is counted, right? So when you have a zero show up more than once, you count that as more than one zero. So if we have a degree 7 polynomial, we're going to have 7 zeros, but some of them might be repeats, and also some of them might be complex. So here are some examples, just really quickly, to see, how we keep getting the number of zeros that matches the degree of our polynomial. Sometimes we have multiplicity, sometimes we have complex, right? But you see the pattern holds. Okay, how about finding some zeros that have been, well, we can work backwards too. We can find polynomials given certain zeros, right? If they tell us that we have a polynomial of degree 4 with these 4 zeros, and then they also have to give us one more point, because with those 4 zeros, we actually have an infinite number of polynomials. Because this first step, as you can see, is we just create factors based on our zeros. So x minus each of our zeros. So we have x minus I, right? X minus a minus I, x minus 2, and x minus a negative 2. And then we clean those up, right? This becomes x plus I, and this becomes x plus 2. Now, when you have an a minus b times an a plus b, we know that that just gives us a squared, right, minus b squared. But in this case, minus I squared, remember I squared is negative 1, so we get minus a negative 1, which becomes plus 1. That's where this piece comes from. And then, of course, x minus 2 times x plus 2 gives you x squared minus 4. That's that difference of squares rule that we know. But you still have this a out here, right? I told you there are infinitely many polynomials that are going to have these 4 zeros, because this a could be any non-zero constant. So we need this last piece of information to kind of specify what a has to be. And it's very simple. Once we get it to this nice little pretty form here on the second line, then we can multiply out all that stuff, right? So we basically kind of foiled those two factors. And then now we have our polynomial as it sits without the a. And then we know p of 3 has to equal a certain thing, right? It told us p of 3 has to equal 25. So that means if we plug in 3 for our x's, right, then the answer has to be 25. So we plug in 3 here, 3 here. We do all this work. It comes out to be 50. 50 times a has to equal 25. So we divide both sides by 50. And we get that a has to be 1/2. And so now if you take this a equals 1/2 and distribute it through, you get 1/2 times x to the 4th. 1/2 times that negative 3 becomes negative 3/2, right? And then 1/2 times negative 4 gives you the negative 2. So now this is one specific polynomial with these zeros, but it also satisfies this last condition. So we found the one and only one polynomial that fits all of those rules. Okay, if we were going to do this one, it's really the same thing. They tell us it's a degree 4. They give us a 0, and then another 0 with a multiplicity. So now let's look at how that works. We have the multiplicity 0, and then the regular one. We clean this up, right? Make it a square. And then, of course, that just becomes x. We FOIL out this big piece, right? That's that cubic that, if you don't remember it, there's a nice pattern for it. And if you don't remember that pattern, just, do a plus b times a plus b, FOIL that out, and then take that answer and multiply it by another a plus b. It just takes a little bit extra work, but you can get there. Then the last thing to do is you bring the x all the way through. So here we are. Since we weren't given any information about, it's q of 3 equals something or q of 7 equals something, then we can choose any number for a to give us a polynomial that will satisfy the rules they gave us. So we might as well make a as easy as we can and just let it be 1, and then we're done. Okay, so sometimes they'll give you enough information to solve for a specific a, and if they don't, just let it be 1. All right, complex zeros always come in conjugate parts. This is only helpful because we know that if we find one complex zero, we have to have its conjugate. All right. Here's an example, and we've already seen in our examples before of all of these things that had complex numbers. You may have noticed that they always had pairs, right? I and negative I, 3i and negative 3i. I think we had one earlier that also had two complex numbers in it. So they'll always come in pairs. And if you think about the quadratic formula, you'll kind of see why that is, because the quadratic formula always has that plus and minus the square root piece. So that's where you're always getting those conjugate pairs. So here's one example. They tell you that you have a polynomial of degree 3. It has a 0 of 1/2 and 3 minus I. But because you know this neat little rule, you know the third 0 has to be 3 plus I. And then it allows you to actually create your polynomial based on those specific things. Now, again, they didn't give us any information about what a had to be, so we could have let it be 1, but we decided here to let it be 2 because then that gets rid of our fraction, because we just don't like fractions, right? So we're just going to multiply everything through by 2 to get rid of that fraction, and there's a polynomial that satisfies the zeros that they gave us. Okay, linear and quadratic factors. Linear factors are what we're used to seeing, right? Those are things that are x plus and minus a constant. And those are irreducible. We can't reduce those any further because we have no power of x. So those factors are done. Quadratic factors are exactly what they sound like. They're just factors that are quadratic, i.e. they have a power of x that's x squared, right? They have a power of 2. And we know that when we have a quadratic factor, we have a quadratic. And when we have a quadratic, we can get its zeros, right? We can reduce it one of two ways. We can either factor it if it factors, and oftentimes it does, and if it doesn't, we use the quadratic formula. So that just tells us that when we're doing all this work trying to factor down our polynomials, as soon as we've pulled out enough linear terms so that the remaining polynomial piece is quadratic, i.e. a power of 2, then we stop at that point. We no longer have to do the long division and the syntactic division and the hunt and peck and all those guess and check things. Instead, we treat the quadratic like we always treat it, and we either try and factor it or use the quadratic formula. Now, this is just telling us that every polynomial can be factored into a product of linear and then irreducible quadratic factors with real coefficients. But if we want to allow for complex numbers, then it can always be factored out into all linear terms because every quadratic can be factored into two complex, right, complex conjugates if it can't be factored into normal regular terms, okay? So if we're going to allow for complex stuff, everything kind of gets simpler as far as the rules because everything always goes down into linear terms. Here's an example of a quadratic that, a polynomial that factored into two quadratics. And this one would be very easy to see if you remember to think about these things, right? When you're looking for a quadratic, you're looking for something here on the middle term, and then this piece has to have that same thing squared. So you can see that we have x squared, and then this is x squared squared. So it fits a quadratic, right? It's really of the form something squared plus 2 times that something minus 8. And so that we know that we're looking for factors of 8 that have a difference of 2. So 4 and 2 is pretty obvious, right? So we have square minus 2 and square plus 4. But what was inside that square was x squared, right? And that's where they got this. And now you look at this and go, hey, these are quadratics. Let's try and factor them. Well, this is a difference of squares. It's just this isn't a perfect square. So that's just going to be x plus the square root of 2 and x minus the square root of 2. That's easy. This one isn't perfect square, the difference of perfect squares, because it doesn't have a minus. So instead you think, well, if I set it equal to 0, right, x squared plus 4 equal to 0, that gives me x squared equals -4, which gives me x equals plus and minus the square root of -4. And you go, uh-oh, that gives me an imaginary number, right? That's plus and minus 2i. So if we were not living in the complex world, then the lowest we could reduce this thing would be x plus square root of 2 times x minus square root of 2 times that quadratic of x squared plus 4, and we'd be done. But if we're allowed to go into the complex world and give imaginary answers, then it would reduce down further to, right, x plus 2i and x minus 2i. And that's what we're talking about here, right? If we had to stop in the real world, i.e. world dealing with only real numbers, we would stop here. If we're allowed to use complex imaginary numbers, then we'd be down here at the very end. So it all comes down to the same thing, guys. Use those simple 3 steps. Figure out your P's and Q's, figure out all your possible zeros, start trying them with guessing and checking using long division or synthetic division. Once you get it down to a quadratic, then either factor the quadratic or use the quadratic formula. And it's that simple. Sure, there are some that have shortcuts, but if you don't see the shortcuts, just tackle it with the same skills you do with all the rest.